Okay, guys, real quick. In the unlikely event we have a ice day and I'm trapped at home and can't get to school, I put together a very quick lesson on impulse momentum. We're going to slightly out of order, but not really. So this is a follow-up to our egg against the sheet discussion where we looked at we can change the momentum of an object, the MV, if we apply a force over time. So I think you had a very simple homework problem on this. What I want to do is I want to go in a little more detail. UConn typically sends a question like this, and I think they do this year. You're going to get a problem where we're going to look at a ball being thrown horizontally at a wall, and the ball bounces off. And we're going to take a look at this collision. Now, we're going to study collisions in more detail later, but collisions can either be elastic, things bounce, or they can be inelastic, they don't bounce. It's kind of the happy, sad sphere thing I showed you before. We'll talk about the word perfectly later. So remember, whenever you apply an unbalanced force to an object, the object's going to change its motion, change its velocity, and therefore change its momentum. So an impulse occurs. And again, we have to be careful about these pictures now, these problems. Now, the one thing I mentioned before is that you have to be really careful with direction. Momentum is a vector quantity. If you don't treat it like this on these problems, you're going to get the problem wrong. So you have to be careful. So here's the question. You take a minute to pause the video and jot this down. You want to have a good example in your notebook. We're going to take a 0.25 kilogram ball. We're going to throw it horizontally towards a wall in a particular direction at a certain speed. It's going to hit the wall, bounce off, and come back. And we want to look at what happened as a result of that collision. So again, pause the video, copy this down, and I'm going to work through the problem down below. So the way I do this is the following, and this is kind of the convention. I'm going to minimize this. The convention is to pick a coordinate system. And we're going to pick the coordinate system that you guys are familiar with. We're going to, just like in math class, the number line, we're going to say anything to the right is going to be positive, anything to the left is negative. So if I'm going to the east or to the right, we treat it positive. If I'm going to the left or to the west, it's negative. And same thing with the number line up and down, we typically take positive. Sorry, up we take positive and down we take negative. So the first thing you have to do is you have to draw a picture of what's happening in this scenario. So I'm going to be clacking here with my pen. So I'm going to tell you. If I take my pen, we have a ball coming in, thrown at a wall, hits it. The ball's moving to the west. It hits the wall and bounces back to the east. So I'm going to draw a wall here. I'm going to draw the ball coming in. And the ball has a mass of 0.25 kilograms. The ball has an initial velocity of 25 meters per second. Now, this is the key. It's 25 meters per second, but because it's traveling west, you need to insert the negative sign. That's the vector nature. So if we're showing that this is a negative or a westward velocity, we indicate the direction by using the negative sign. And again, if you leave it out, you're kind of in trouble. The ball's going to strike the wall, bounce off, and come back out. So obviously the mass of the ball didn't change, but clearly the direction changes. And it turns out, in this case, we're asking what's the final velocity. Now, we discussed this before. We said if it were perfectly elastic, if no energy were lost anywhere, the ball would come out exactly at the same speed. And that never really happens. There's nothing that's really perfectly elastic. So if the velocity came out at 25, that'd be great, but it doesn't do that. So we want to calculate what's the final velocity. The other bit of information we need is the force acting on the ball. And again, you have to read this carefully. It says, as a result of the collision, the wall exerts a force back on the ball of 3,500 newtons. And the time it took for that interaction, it's like throwing a sheet into the egg into the sheet, it took time for that to occur. The key is that the force is back on the ball from the wall. So it's going to be pointing to the east. So the force is going this way because the wall is exerting a force on the ball. So because that force is pointing to the east, we treat that as a positive force. You don't have to write the positive sign, but it's important to realize that it could be negative if we're going the other way. And the other thing they tell us is the delta t for that application of that force is 0.003 seconds. So now the problem turns into a plug and chug, but again, it's not a difficult problem as long as you make sure you pay attention to the sign conventions. Because the velocity initially is west, we have to negatize that. Because the force from the wall onto the ball is positive, we can put a plus 3,500. And I expect my answer to come out positive here. Now, if I do the calculation, I'll try to squeeze this in here. We have our change in momentum is going to be m delta v equals f delta t. And we have everything except for the vf. So I have to break this out to say m. Remember, delta is always the final minus the initial. equals F delta T. You do have to factor this through, so it's going to be mvf minus mvi equals F delta T. Then I have mvf equals, just bring the mvi to the other side, so it's F delta T plus mvi. And we're finally at the point where we can simplify the equation. We extend the page here a little bit. So I'm going to solve for Vf equals F delta T plus mvi over m. Now when I put the numbers in, again, because the ball is bouncing off, it's going to go to the east. I expect this to be positive. So 3,500 is my force. My time in action on the ball was 0.003. My mass of the ball is 0.25. The initial velocity, again, was negative 25. That's important. And then again, my mass will be 0.25. Now, when you do that, I believe when you actually solve for this, you'll get a VI equal to 17. And again, because that's positive, it's implied it comes out positive, then the direction, because again, these are vector quantities. The velocities are vectors, the forces are vectors, so we need to treat them that way. And then we can say it's east. So the ball bounces back to the east. And again, the question we asked was this perfectly elastic? Well, of course it's not perfectly elastic because it came off at a different speed. And again, nothing's ideally perfectly elastic. There's some things we model in physics, like the behavior of gases in chemistry colliding together. We treat those as perfectly elastic, but in real life, we normally don't. So this type of problem, again, you can pause the video and jot down the notes on how to do this. They're not difficult to do, but you have to be careful. And UConn typically asks this question, and I think this year is a typical year, so it's an important one. Now, all the problems are kind of the same. You know, these are very common questions in physics. Well, first of all, was there an impulse? And what I'm really asking is, did the momentum of this ball change? Well, yeah, the ball had momentum of 20 to the west, negative 20. It bounced off. It's going to have a different velocity. The mass doesn't change. So, again, there's an impulse. Whenever there's an impulse, there had to be a force acting in some period of time, and you can calculate that just like we did a minute ago. I'll leave that for you to do. But it's the exact same problem. We'd have to negatize the V, keep this V positive. Again, the force on the ball is, in this case, is to the east. So there's an impulse, and you can calculate the new force. Now, just be careful. Again, I just made note of this. Be super careful to make sure you treat the vector nature. Even though I say it 100 times, somebody always does a problem by leaving everything positive, and they get the wrong answer. So you need to remember to make something that's westward negative and something that's eastward positive. Now, again, just be careful. This can also act vertically, and it can be flipped around. So, again, did momentum change? Yes. Did momentum change? Well, this problem, I have a 2 kilogram ball coming in going 5, and it bounces off 2 kilogram ball traveling 5. It doesn't look like it changed. Everything seems to be the same. Momentum is 10, momentum is 10. Unfortunately, the momentum did change because the momentum here was minus 10, and here the momentum was positive 10. So it actually changed by a factor of 20. So again, you have to be careful. You have to pay attention to the fact that what's the vector going in, the momentum vector going in, which is 10 long, and the momentum vector coming out, which is 10 long but pointed in the other direction, is a different vector. Now, again, we will talk about this more. I wanted to make sure you had something to do. If in the unlikely event I can't make it to school, we will obviously move our bungee contest till next week. But go ahead and try homework 3. There's a problem on the front, very similar to this. There's a related problem to the egg drop with Lana stealing eggs. That will give you a little more practice for the egg drop contest. So go ahead and try that. We'll see how that goes, and then when we get back, we'll do the bungee contest. All right, enjoy your snow day.